So this is our second video to prove Kepler's first law. In the first video, we proved that the orbit of the planet was on the plane. So we proved that by proving precisely that the r cross the position r's position cross its velocity is constant, and so we know this vector c is constant. And so because it was on the plane now, you can take the freedom and say, okay, why don't we just put that constant vector to be in the direction of the z-axis, so I call it E3, and so k is its magnitude. So the magnitude of c is k. So we're going to try. We already know that. So we knew it was on the plane, and all I need to do now is make it the xy plane, and the normal vector is going to be the third direction, the perpendicular direction of the xy plane. Now, the r was the position vector, and I was calling u the unit vector in the direction of r. So when I write it with hand, I'm going to put this magnitude of r. 1 over magnitude of r times r is going to be the unit vector in the direction of r. So this is what's happening here. So if you want to have a picture, it's not great, but I'm having my x, y, z coordinate system. I have a curve that goes somewhere here. It's on the plane. And then these are my position vectors, r, if you think of them like that. Okay? And I'm assuming that the sun is here, right? The sun was here, and my planet is moving somewhere around here. So I want to know what kind of curve this is. I don't know what's an ellipse. We're going to prove that. Okay, so I'm going to use two things in this for these part, and one of them we proved. We proved that if you have a curve, in this case r, of constant magnitude, let me not call it r because r is not constant magnitude, but if you have curve gamma with constant magnitude, we proved this in the other video, then gamma prime is perpendicular to gamma. Okay. And this one we proved in the other one. What we didn't prove is this one, but we're going to, it's something you can prove in a Calculus 3 class, properties of a triple product. So you have u cross v cross w, so the cross product of three vectors. You can write this like a u dot w, this is a scalar, right, times the vector v, minus u dot v times, this is scalar, times the vector w. So this is what we need to check. Okay, so u dot wv minus u dot vw. So we're going to use those two things in a minute. So let me put this here in the corner. Okay, so let's start. So what I know is that and something else we said we're going to use is we had from before is that we had Newton's second law, which gave us that the acceleration was negative gm over r cubed magnitude r. So if I write u in this form, I have that this is, so if u is this and r is that, I can write this like negative g m, I have r cubed here, but my r, I can write it now like magnitude of r times the vector u, so then I really have that a is negative gm over r squared, magnitude of r squared, times the unit vector u. Okay, and this is something else that we're going to use in a little bit. So let me keep that in the corner here for later. I don't know if I use it like number 3, but maybe I'll need it labeled. Okay, so let me erase this here to get some space. Okay, so what are we going to start doing? So let's start with this. So we know that r is, I just wrote it here, like I use it for the a part, is the magnitude of r times the vector u. So I have a scalar function, the magnitude of r times the vector function u. And here the dot product also works. It was written before. In video 1 we talked about it. So this is, if I take the derivative of this thing, if I take the derivative of the vector r, it's going to be the derivative of r, the magnitude, times the vector u, plus the magnitude of r times the u prime. Okay, so I'm not writing anything fancy here, but just the left side, the derivative of r prime, so sorry, derivative of r is v, so it's called that v. So it says that the velocity vector is magnitude of r derivative u plus r u prime. Okay, so let's keep that here on the side. And this right something else. So what I want to do now is find out my vector c. So let's write my vector c that's written here. So I know that my vector c is r cross v, right? And I'm going to find my new way of writing v. So this is my vector v. So my vector c is going to be r, which the new way of writing r, for instance, is magnitude of r times the vector u. Okay, and now how about this new vector v is going to be what I have over here, right? So I'm just going to probably make it look like this. So this goes in here. Okay, so I got ru cross r prime u plus magnitude of ru prime. And now we use the distributive property of the cross product, which is a strong one. So when I write, this is the magnitude of r vector u cross the vector, you put it like this, cross the vector, you put a parenthesis here, magnitude of r prime u. Okay, these are vectors, of course. And then plus, again, r u cross the vector magnitude of r u prime. Okay, so now here, look at this for a minute. This is a scalar, this is a stretch of the vector u. This is a different stretch of the same vector. So I have a vector cross a product, cross a scalar of the same vector. That's 0, right? So this is a 0 because u cross a multiple of itself is 0. Good. And so only this part survives over here, and so I get my vector c to be, and this is a scalar inside. I can take it outside of this, so I get the magnitude of r squared u cross u prime. Okay, that's what I got. This is the scalar part. It's just multiplying its magnitude, and this is u cross u prime. Okay, so we got this far. Okay, now notice that I'm going to go over here and say we can also write, I'm also going to write, what I had was r cross v. I'm going to do something different right now, a cross c. Why? Well, we'll see in a minute. So I'm going to write a cross c. I can write, like, remember my vector a, I wrote it over here, is here, negative gmu. So let's put it in here. Gm over magnitude of r squared times the vector u, that's a, and then this cross c. But c, I'm going to write it like, I just wrote right here, r squared u cross u prime. Okay, so I have the magnitude of r squared u cross u prime. And here I'm going to use this property. So let me grab this one from here. Just paste it over here to know what I'm doing. So I'm going to use this property. So I have the triple product. I have a vector. This is like my vector u. Sorry, this is like my vector u. This is like my vector v. This is like my vector w, right? So just follow the pattern, and it's a little bit overwhelming, but we can get this. So the first one says u dot w, so it'd be this red part, negative gm over magnitude of r squared u. Dot w, I'm reading this part, and w is this vector, so u dot u prime. And then that scalar multiplies the vector v, which becomes the vector here, r squared u. So I'm going to have here r squared u, and then minus, I'm going to have u dot v, so it's going to be, again, this red part, negative gm over magnitude r squared u, dot the vector v, but in this case the vector v is u again, so I'm going to put this u, and then close that parentheses, and then times the vector w, which becomes, in this case, my u prime. Okay, oh sorry, and it has a scalar of r squared, which is coming here, so I need that scalar of r squared. So now a few things happening here. I have, this is u dot u prime, and in this case I'm going to use my first thing I wrote here. If you have constant magnitude, then the derivative is perpendicular to the position. U is a unit vector, so it had constant magnitude, so this is 0. Okay, so this is 0 because of that. So what survives here is that A cross C equals, get a double negative, so it's a positive gm over magnitude of r squared. U dot u is a 1, right? Because it's a unit vector. So you just have the magnitude of r squared u prime. So of course the r squares cancel, and I get that A cross C is gm u prime. Okay, I'm going to write this like, or A cross C is the derivative of gm u, just because it looks a little bit nicer what we want. Okay, so we got that. Now, one last thing in this part is to notice that that if I take the derivative of v cross c, this of course is just the product rule again, v prime cross c plus v cross c prime, right? So this is 0 because c was a constant vector, so this part is 0. So this appears, and then we just have that the derivative of v cross c is a, right? The acceleration is the derivative velocity cross c. Oh, no, we just got. We had acceleration cross c was exactly what we had here. So if I put those two guys equal to each other, I really end up having that the derivative of my gmu is equal to the derivative of the v cross c. So if the derivative of one thing is equal to the derivative of the other, means they differ by a constant, right? So we're almost there. We have that g, let me write it backwards. The way we want to write this is that v cross c is the gmu plus a constant vector, we call it d. Okay. So I'm going to stop here for, I think I don't have a video limit on, time limit on YouTube, so just in case I'll stop here and in case I have to edit, but I'll continue recording. Okay, so I have this, and if I need to continue just one more, my goal is to make this, use this, remember our goal is to find that R is an ellipse. So this vector G is a constant vector. So why don't we make that, we can take the freedom and say, let's make D, or assume D, is I'm going to write D without the arrow, and this is E2. Sorry, E1. I want to go along the x-axis, so that's going to be E1. Okay, so D is the magnitude of the vector D. It's a constant vector, so I'm assuming it's that. Okay. So it's along the x-axis. So my E1 means x-axis. So if I take, why am I doing this? Because so if I take R dot D, or it's going to be the magnitude of R, magnitude of D times the cosine of the angle theta, and theta is the angle, right? If I had my y-axis here, and now my R is going something like this. This is my position vector R of t. My vector D would go something along here. So the angle between them is exactly the angle which we use for polar, because the equation we're going to get is going to be in polar coordinates. Okay, so what's going to happen now? Well, why don't we just write who is the magnitude of C? Remember, the magnitude of C is the vector in the third direction, so I'm going to write C dot C. So I'm going to write C in two ways. I'm going to write, sorry, not two ways. I'm going to just write C dot R cross V, right? Now, what was the C was? So now, this is a triple scalar product called sometimes, and remember, this is just a determinant. If you think of this, it's really the determinant of putting the C vector in the first row, the R in the second, and the V in the third one. So if I swap rows here, the determinant changes the sign once. So I'm going to swap the rows once and put the R outside and put the C in the middle. And by doing that, I should change the sign, because now what happened now is I have the R on top, the C in the middle, and the V in the bottom. Okay, that's negative. And now, because I'm going to use what I had over here, I had an expression for V cross C. I have here C cross V. So I'm going to swap the order one more time inside this, parentheses, the cross product. So it's going to be V cross C. But that changed the sign once again, so it goes back to plus. Okay, so this is the same as that. R dot V cross C. And now, what I'm going to do is write what I had over here. So this is, and I'm going to write, instead of this was a vector C, I'm going to start writing C without vectors, without arrows, and for the constant, like I did here for the D without the vector. So this is going to be R dot, and V cross C was GMU plus D. These are vectors still. So distribute, and I get that, sorry, this is C squared. So I get R dot, let me put the scalars first. So I should still put arrows for these guys. So I get GM R dot U plus R dot D. Okay. So this R dot D is really what I said up here, right? So I really have G M R dot U, and R dot U is the magnitude of R, magnitude of U times the cosine of the angle between them. And R dot D. Sorry, I don't want to write that. In this case, I just want to write it like this. The R dot U, I just want to write the magnitude of R U dot U, right? This is R. Okay? And this case, I'm going to write R dot D is what I have up here, magnitude of R, magnitude of D, cosine of the angle between them. So this is a 1 if I see this part is a 1, because U is a unit vector. So I get GM magnitude of R, and over here I have magnitude of R, magnitude of D, cosine theta. So now I'm going to start writing just RDs without arrows. So I'm going to copy this and have it cleaner without. So now I can imagine all these things are scalars, so I can start forgetting about these arrows if you want. So I really have c squared, sorry, this was c squared. And write, I'm going to factor this r is the magnitude of r, okay? And I have a gm plus d cosine. So solve for the r, and I get that it's c squared over gm plus d cosine. Okay, so this is, I'm going to start right here. This is as far as I'm going to get in the video. Now, there's some work to do to transform this to Cartesian, or to make it look exactly like the polar version of a conic section. But this is a polar version of a conic section. The general form is, you have to interpret this in terms of whose eccentricity and so forth, but this is a polar equation of a conic section. Then the only option for having a closed curve is an ellipse. So this is an equation of an ellipse, and we are done. This is the